Hello, this is Mr. Huff, and this lesson is brought to you by lots of coffee and probably some Pop-Tarts. This is Antoine Lavoisier, and he is known as the father of modern chemistry. He is the one who named oxygen and hydrogen, and even though he didn't have a lot of sophisticated science equipment, he did learn a lot of things about how chemistry worked. This is an example of one of the experiments he may have conducted. So here we have a candle burning inside a closed glass container, and we know how much it weighs. And he noticed that whenever you burn the candle, even though the candle burned, it changed appearance. It looks like there's less of it. If you close that container, you have the same weight before and after the reaction. So he came up with the idea of the law of conservation of mass, which says the total mass of the products of a chemical reaction always equals the mass of the reactants. You can't create or destroy mass, but you can move it around. So here's another definition for you to think about. A chemical equation is a way to describe a chemical reaction using chemical formulas and other symbols. When you are looking at chemical reactions, you will see this little arrow in the center, and this arrow means produce or form, or produces or forms. And in this case, you have reactants that produce products. So reactants are on the left side of the arrow or opposite the arrowhead. The products are on the right side of the arrow, or the side that the arrow points to. This is another way to look at a chemical reaction. So we see here, we have the pictures of the different molecules that are participating in this reaction, and on the bottom we have the formula, the chemical equation down here. So we're saying 1 molecule of methane plus 2 molecules of oxygen produces or forms 1 molecule of carbon dioxide and 2 molecules of water. And when you look at the graphic representation here, you see an equal number of shapes on both sides. Consider the methane molecule. It has 4 hydrogens and 1 carbon. On the other side, you see 4 hydrogens and 1 carbon. On the reactant side, you see 4 oxygens, 1, 2, 3, 4. And on the product side, you see 4 oxygens. So there's an equal number on both sides. Think about sandwiches for a second. Suppose you were going to make sandwiches for a picnic. You know that each sandwich needs 2 slices of bread, 8 slices of turkey, 3 slices of cheese, 4 slices of tomato, and 1 big leaf of lettuce. This is my kind of sandwich. If you also know how many sandwiches you need to make, you can figure out how much bread, turkey, cheese, tomato, and lettuce you need to buy so you do not have any food left over and you make a complete sandwich every time. Making sandwiches can be compared to chemical reactions. The ingredients in the sandwich are the same as the reactants in a chemical equation, and the finished sandwich is the same as the products in a chemical reaction. So the number of pieces of bread and turkey, cheese, tomato, and lettuce, those are the coefficients of the reactants, and the number of finished sandwiches is the coefficient of the product. However, the quantity of each ingredient is the same in the reactants and on the product side. So the number you start with and the number you end with have to be the same. You may see some other symbols. We've talked about the arrow so far, and we've seen the plus, and that's pretty obvious. But you may see these lowercase numbers, lowercase letters. That means solid, liquid, or gas. You may also see these little parentheses around AQ, and that means aqueous, which means it's dissolved in water. And sometimes above the arrow, you may see heat, you may see light, or you may see electricity, and that just means you have to add some energy to get the reaction started. So you heat them up, you expose them to light, or you apply an electric current. So here we have reactants and products. Notice that you see everything we've talked about. We see the chemical formulas. We see that this is aqueous. We see coefficients. It's aqueous. We see a chemical formula. We see a coefficient. And we see a coefficient, and it's aqueous. And also we have the arrow that shows produces or forms. The way you would describe this equation is this. Nickel 2 chloride dissolved in water plus sodium hydroxide, also dissolved in water, produces solid nickel 2 hydroxide plus sodium chloride dissolved in water. Notice that the coefficients show the number of units of a substance taking part in the reaction. So we have 2 of these and 2 of these. This is what that equation looks like graphically. So we have nickel chloride plus 2 sodium hydroxides produces a nickel hydroxide plus 2 sodium chlorides. And at the bottom you can see the equation. And at the top you see the equation. So what does a balanced equation show? It shows that we are paying attention to the law of conservation of mass. It only changes the way that the reaction is represented. It does not change what happens in the reaction. And when you're balancing an equation, you only change the coefficients. You can never, ever, ever change the subscripts. So if you had 4 hydrogen molecules, that's 8 hydrogens, you would not write that as 8H or 8 hydrogens. It's 4 times H2. H2 is a diatomic, so it's 4 of those, not H8. Don't change the numbers at the bottom. When you change the numbers in the subscript, you're actually changing the chemical compound. You're changing what it is, and you can't do that. You can only change the coefficient in the front. Keep in mind that a balanced reaction has the same number of atoms of each element on each side of the equation.